And good morning to everybody. Thank you so much for the opportunity to share my passion, my hobby, my topics. Today we're talking about building artificial intelligence recommenders using Microsoft machine learning. So I started working in artificial intelligence in 1989 at IBM, and it was that kind of black science. How would I define artificial intelligence today? It's very simply what only humans used to do. And this will continue to evolve all the time. And to give an example about the fact that artificial intelligence is doing that, I want to share the story of John, the expert. He used to work at Blockbuster, and he used to recommend every movie. And in doing so, he was upselling, cross-selling, and making the user, the client, feel welcome and build the entire business for Blockbuster. Well, he has been replaced. So there are tasks, jobs that what humans used to be that today can be done better by machines because we can analyze more data, giving more precise recommendation indication. So machine can predict what you want, and we call it recommender system. What is this about? This is about to know when you feel a need, a desire, a wish, even before you know. I mean, Netflix is proud to say that they know what movie you're going to like before you even know that you're going to like. This is a topic and a differentiator factors for many sectors. Amazon has made sure that when you go shopping there, for one item, you don't leave the site without buying 3 or 4 items. And when magazine propose content, it's all based on recommenders, so that there are things you like, and therefore you increase your stickinesses and they can sell more advertising. But if you think this is only in the virtual world, that's not true. If you use some of the MapQuest or Google Maps and you let them recommend you where you can stop for something that you like in the way there, they do it, and they impact your real life. If you go to Match.com, you're going to meet the right person in real life. That it's all based on recommenders. And we all probably use that. I mean, Coursera will recommend you the next class before you're done with your current class. So there is application in every sector. And there are applications that are really, really deep into business. This is an example of an agent, a sales agent dashboard that look at the client trying to upsell new services and looking at the client situation. In this case, you have a client that has bought a lot of appliances, and you know the information about age, reward points, and events. And at the end of the day, you have the recommendation at the bottom that is, since it buys a lot of appliances and is definitely in its chart more into the house, let's offer a free design consultation. Or given the fact he has been reacting very well to reward points, let's give some extra points for certain desired behavior. So this is a courtesy of Neo Analytics, but this is another example of recommenders for business. So any company can use this as a competitive advantage. And if we feel that this is far out, well, I want to share with you Deloitte Touche report based on a survey. They believe that this year will be about 65% of the corporate enterprise application using cognitive science, and by 2020 will be 95%. So this is happening. It's worth the investment of time to become really good at it. So now, what is the logic behind a recommender system? How can we predict how that particular user will rate all of those movies he has not actually seen It seems like a daunting challenge. Well, it is not. Let's go through the details. The first technique is called item-based recommendation or filtering. And this is what you generally see in a website with the concept of related items are, or this is what Netflix proposes you when you're are interested in watching a movie and tells you the related movies are. How this works. Okay, there is this one, that programmable. The target question we're trying to address is what is the related item to the movie Cars in this case? And let's look at the data we have. So in most cases we have the movies and how people are rated. And for this exercise, since it's item based, let's assume that those names are generic, unknown people, but the only thing you know is that the person that watched Cars and rated Cars 1, they also rated Dark Knight 1. The person that watched Cars and rated 3, they rated Dark Knight 3. Now the question is a related item, can we predict how Dark Knight will be rated? Of course, we can, and that's the way we do related items. Another approach that is more sophisticated and used by advanced systems is the one based on users. We try to understand people and we let people tell us what they like in exchange for a better service. So when you log in into a site like Netflix, they ask you to rate those elements, and they ask you also to pick some characters. So we avoid that if somebody else is using your computer, the system does inaccurate prediction. And this, by the way, allows the fact that there are family dynamics of traits and there are individual traits, and they all combine to make the most accurate prediction. Now, in the user-centered recommenders approach, the target question is, will user, in this case Joseph, like the item Dark Knight? Now, we look at similar users. So we switch. We don't look at a movie that were rated the same way or similar way. We're looking at people that behaved and liked the same way. So in this case, Carmen has a latent behavior that is similar to Joseph because he rated the movie Alien and the movie Backlash the same way. Well, the algorithm will extend the common pattern saying that if Carmen rated Dark Knight 1 and didn't like, very likely Joseph will rate it the same way. So far I hope the situation seems quite simple. Now, Netflix launched a worldwide contest with a bounty saying, challenge people to build a better recommender system for Netflix data, address the accuracy for new items and foreign items. The issue about new items is that we don't have much data, so we don't know either by user or item what is going to happen, and this foreigner, we still don't know in another market how people will rate and like it. So the question is, will new user, Joseph, like new movie, Dark Knight? And since generally the new movie and the new user are the most important part of the business, you can understand that it was worth for Netflix and for other vendors to invest a lot of money into that. And in general, in any other business, this challenge would apply. So assuming that you have missing data, all you do is you use the crowd's votes to complete the missing entries. So you start to harness all the information, try to find synergy to come up with something like this that is called matrix factorization. So you have approach A using user-based, approach B, so approach A item use, approach B user-based, plus leverage the data, and you start filling in all the information you don't have by combining them. This is what the humans might call it intuition, in the sense that we actually, let's give an example before I go deeper into that. The example is, we are going to try to determine the latent feature for an item and for a user and correlate them. So what we do is, first we look at the degree of scariness or kiddiness of a movie. In the example I'm about to analyze, let's analyze the fact that we want to compare a movie like Cars, Dark Knight, and Alien and Cars, and consider them for just simplicity, that those movies are half scary, half kiddiness, because they are watched by a younger family audience, and both Alien and Dark Knight are a little bit scary or racy and so on. Then we look at the attitude of the user Esmeralda. The user Esmeralda has an attitude to give 5, so like scary movie, and has an attitude to don't like the kiddie movie. So we combine the information of scary and kiddie with information of the movie, and we calculate the expected rate in this way: 5 times half plus 1 times half, and we get the expected projection. Now, this might seem quite simple when we have 2 movies and 2 users and we make some assumption. What is going to happen when we have millions of users, millions of movies, and millions of data missing because the movie is new? Then you need to look at some applied mathematics. And this is what we are about to discuss today. It is the matchbox algorithm. So what we want to do is identify the latent trait space. So in a chart, what we do is we chart the item that was rated positively by a certain user, and if we find that a certain user has a sequence of items that he likes to watch over times, we look this as a cone. When we see that certain cones start to, the vectors in a cone start to align, means that we are really able to project the user capacity to like the next. But at the same time, when we see 2 cones next to each other, we can say that what this user A is going to like next is going to be something similar to the other cone on user B, and this is commonality of space that are called traits. The extraction of this capacity to see the cone through the data is the latent feature. So the capacity to see this person likes the scary movie. So it's not like Dark Knight. It's just, or Cars. It's just the essence, the intuition that the human generally has that this kind of movie is not going to be like that person because that person doesn't like or like scary movies. So that is what the machine has now gained the capacity to learn. And the possible applications are multiple. The fact that we call them recommenders, in my opinion, is very limited but useful. Now the question is, by now we know what it is, how do we build one? Well, it used to be very complex, but fortunately, with the latest release of technology from Microsoft Azure Machine Learning, things have got way easier and way feasible. And let's go through this. Well, we have the typical process that is in a data project. Load the data, explore the data, engineer the features, build the models with algorithm, and deploy the model. One thing that is very often neglected is the fact that you need to architect it. So to architect it, the way we work in my team is we base our work on habit number 2 of Stephen Covey. You know, Stephen Covey is the author of the book, The 7 Habits of Very Effective People, and his number 2 is begin with the end in mind. So the first thing we do is, what is the service going to look like in the user scenario? And for example, in this case, is the opportunity to have a suggestion. Well, we don't even call it, so a personalized suggestion just for you. Look how strong this personalized suggestion just for you, top 10 for Angela. So if that is what we expect, how we process the billions of data to make something that is personalized for this user, Angela? So we need a very powerful system. And this is generally what you generally would build with hundreds of business analysts that will study possibilities, but no longer. What is happening is there's a revolution. You don't need analysts now. You need the data. You have something called machine learning, and machine learning is a scientific discipline that explores the construction and the study of algorithms that can learn from data. Such algorithms operate by building a model based on input and using that to make predictions and decisions. So no longer tons of pages of business analyst chart. We look at what is the reality and in the complexity of years of data and extrapolating latent trait from different type of source of information, and we make prediction. Now, let's go through the step-by-step on how we do this with Microsoft Machine Learning. In the loaded data, we're going to see certain tools that are specialized for that, and we're going to go into a demo and see them one by one. Then we're going to do engineer the features, so we're going to decide what is relevant, why is it relevant. Is it a classification case, like 3 or 4 values or scenarios, or is it estimating a continuous value or number, and is it yes or no? So that's a part of engineering the features. And then we build the model. It's which algorithm we're going to use, which one is the most precise, and how we visualize the result. So in the demo, I like to first say what you're going to see, and then I'm going to show it. And that allows probably the best clarity around that. So in the demo, you're going to see as data, the user ID, the movie ID, the timestamp, and the rating collect from the stars, the movie favorite you saved, in the sense that when you go in a site you save something, that information are fed to the recommender system. The movie you watch entirely, the one you didn't watch entirely, the one you rewatched. So those are the kind of things that contribute. So the word rating is not just the star 1 to 5. That is a simplification of other processes that happened in the back. And there is also another data set that is very important to distinguish. You work with the data that can be digested and processed by an algorithm. Therefore, you cannot write a movie, The Dark Knight, in plain text. You just need to have an ID 35 that said this maps to this movie in this language and in this release, and so you want to have a separate place where you have the movie mapping the data catalog. That's very important for hygiene to separate those kind of things and to prepare the right data. Then we're going to look into target features. And the 3 elements that are important here are the movie, the user, and the rating. And from this, what we want to prepare for is to prepare for understanding the related item-based filtering. The item for the user means we recommend this item for this user, and this is user-based filtering. And then we do rating prediction for the user. Means how, even if we recommend, is this going to be a 5-star recommendation or a 3-star? And then related users. Why this is important? First, because we can let the user find peers and people like them in Facebook, LinkedIn. The second is because we start to understand patterns among possible new clients. But there is also a very important part, is what is called the second screen. It means that when somebody's watching something, a show or a movie and so on, sometimes on the iPad they are chatting, tweeting, and they want to talk to somebody that is like-minded, as watchers watching the same movie at the same time. Typical technique that was born in video games, but has been developed a lot. I mean, there was a stunning number of this scenario happening during the Super Bowl game, and this year was the year where this became so dominant. Oh, sorry. At this point, once we know the features we are targeting for which objective we build the model, Microsoft makes available as part of the Azure Machine Learning Studio the Matchbox Bayesian algorithm. And as I showed in the previous slide, there is a pointer there with a blog where the scientists that tune the algorithm has written an extensive article to really make sure that you can understand the in and out and the limitation of the powerful capability of this algorithm. And then the deployment. The deployment in Microsoft Machine Learning is a web service. I'm going to show you how it's compiled and can be called as a REST API from the most likely sometimes in doing experimentation is Excel, but can be your Netflix competitor application or your banking services recommendation, anything you feel that will generate value with this backend. So let me switch to the demo here. All right. I hope that it's big enough for you guys to see it. Okay. For this scenario, we have the first data loading tool that is containing the movie ratings. So the way machine learning works is you have here the tool to do a certain specific task, and on the right you have the properties. And you can view the data sets in two ways. You can download, as you can see my screen right now, and open in CSV, or without abandoning here, you right click and you do visualize. And here you have a visualization of what is the data we require. In this case, the user ID with a catalog that maps to the real name, or if you have a PII, personal identifying information limitation, it's okay, that is the user ID, the movie ID, the rating, and the timestamp, because how recent is the valuation, it's very important information. All right, you can view this the distribution of the data as a chart or a block or box chart, and that's it. Then you have what I mentioned before, the capacity to map the catalog. Think about if you're doing books recommendation, that could be the ISBN, for example. And here you have movie ID and movie name, pretty straightforward. The metadata editor allows you to define the data, because the algorithm has a hard time to understand if the number is part of a classification. For example, if you have a number between 1 and 12, you probably mean the month, and therefore you want to treat as a classification, or otherwise you can look at data in a different way. In this case, an integer can be a datetime, a boolean, yes, no. So those kind of information you want to define to help the algorithm to be more precise. So you can make this categorical. The case of if a number is between 1 and 12 and you know it's the month, it's not just alternative. So in this case, for example, the number of stars, this is categorical. You don't have 3.2 stars. Generally, you have either 3 stars, 3.5 or 4. That's it. So those are the category. So the metadata editor allows to prepare the data for the digestion. This point you see here, you join the data from the two catalogs, and you prepare here with the launch column. So here, among all the data available, you decide to include or exclude certain columns, and those are the three variables that in the algorithm is important: the user ID, the movie name, and the rating. At this point, you proceed with another step, that is the preparation of the data for the experiment. And the way machine learning does is you take a certain asset, let's say 80% of the data, and you give to the machine learning algorithm to say, identify an algorithm that will project what I need, and you save 20% of the data to benchmark if the algorithm is really projecting something right. And so we split the data, and when you see here split the data, in this case, we've decided to split 75% will be given to the algorithm, and 25% instead will be sent to the testing and scoring of the algorithm. So when you see here, two departure, you can see here that one departure of data, the 75% goes to the matchbox recommender, and the other, they go to the evaluation recommender. So think about, I'm hiding the data to make sure that I can test with the same good data count, the same population, if your prediction capacity is pretty good. So it's a very, very nice technique. And you can see here in Microsoft Machine Learning, it's quite simple to do things like that. Okay, let's go back here. You pretty much specify here if you want to do 75, 80%, and also you have a lot of other variables for which there is always documentation at the bottom to do what is the meaning of all of them. So there are plenty of algorithms. Some people make a living just out of understanding all. You can every time go and refresh your understanding very easily. One of the things that Microsoft has done that is, in my opinion, quite of a leadership is the capacity that instead of understanding all the variables and testing them and tuning them, has introduced something called the sweepstakes. In the sense, there's a simulator that will try all the possible combinations and tell you which one is the best variables in terms of number of iteration, number of seeds, number of code items used. And when we say code items, it means the items that are completely new and you have no data in this case. And there is a very, very state-of-the-art capacity to make something that was black science now affordable. I feel this is the same way as before introduction of Microsoft Access, database was science for specialists, and it became for everybody, and the same is happening here. Now let's go and see what is going to be done on the data, on the 75% of the data that we are splitting and goes to this box here. This box here is the matchbox recommender. And in this little dot here, we have the opportunity with a right click on the mouse to go and visualize what is happening there. So we are set to training for prediction, and this is the algorithm that this document as a matchbox Bayesian. From this, once the recognition of the functions that will make prediction has been completed, the data are sent to the scoring tool. The scoring tool, after you run the experiment, to run the experiment, you have here the button, this one says run, and that I don't do now, otherwise we'll be waiting for 5 minutes to do this exercise, and it's not good usage. But I did it before we started the demo, so we already have the exercise. And you know from here, on the top right, finish running means that this is compiled. If you make even a small change and you don't compile, you won't be able to see any result, because the result is shown here will be inconsistent with the input represented at the time of visualization. So in this case, we'll be seeing things without modification, and that's why I'm going to do this demo after I compile it, so I can show you the result of this algorithm. So the result of this algorithm is that for one item, let's say the movie Matrix, the algorithm was able to find the other movie that people have generally watched, and therefore you can make a recommendation for cross-selling, upselling, make sure that they consume more of your services. And as you can see here, we have like a certain level of precision that we're able to predict quite well the next second to that. But when we look at backup, if the user doesn't like this and that, we start to have less of a precision. Now, if you remember in the PowerPoint, I set up the scenario for the demo where even if it's the same algorithm, we want to know different things. So this scoring will score the related items. So out of the 4 things the algorithm can do, there is a related item, related user, item recommendation, item prediction. So this is the user-based prediction, the item-based prediction that will recommend an item. If we go here, we are going to score another output of the algorithm. And this item, if I click here, it becomes blue, and I look here, we'll switch. So, okay, this is item recommendation. This is related item. This is item rating. And this is related users. Those are the 4 items that we discussed in the PowerPoint. So when we do item recommendation per user, we go and visualize, and let's see what is this that you get out of the algorithm. Here we get that for user code 2021-9, we're getting that the item that is probably like is this movie. As a backup, you have Captain Phillips, as a backup Star Trek. And as you can see, this is a user-based recommendation. But when we look at other opportunity that the algorithm will give you, that is the rating prediction. So yes, we recommend you to watch the movie, but how likely is that you're going to like it a lot? And we right-click here, we visualize. And here you have that for this user code, watching this item, it's going to be probably a 10. It's going to like a lot, while others, it's pretty much a halfway, you know, but still one of the possibility of things to recommend. And the fourth thing that if you remember in the list, so think about this, you don't even need to remember, you just have the option to choose the opportunity. The algorithm will, if you remember the explanation about the trade space, the algorithm will find in the trade space of the corn the other user that liked the movie and give you a prediction of related users. And if you visualize, you have here the name of the related users to represent an offering to watch on the second screen or to connect with share or with Facebook, or invite also your friends. And very likely, if the invitation is valid, the user will say, actually, yes, he will like it. Let me invite him to Netflix. So as you can see, there are functionalities that are very, very powerful. Now the question is, how accurate is this, given the fact we are rating movies that the person has not watched it? It seems like strange, but in reality, it seems like there are things that are going to happen because we can predict. So the precision is generally represented into the evaluate the recommender. And if we, for example, take the capacity to recommend how much this is going to like it, and we visualize this, you have a certain index of precision that are very specific to certain indexes that will tell you how good or bad. Those are, again, indexes that are, I don't want to, given the time we've left, I'm just going to tell you that there are, the explanation are here, and click for help, and they change for different things. For example, when we want to predict what is the likelihood the user will watch this movie, therefore I propose, I have the sum of probability, in this case is 71%. It's not bad, but it's not excellent as well. So that's another very easy to understand metrics. And for every recommendation, you have evaluation. And you need to make your call, because if you're doing a mailing, probably low probability is still accessible. But if, based on the decision, you may make an investment and lose millions of dollars, so you probably do not accept a 71%, you probably accept a 95, 99% accuracy. So this is all about the business use that you will require a certain level of efficiency. How do you increase efficiency of the algorithm, or precision of the algorithm? Generally is the amount of data, how clean are the data. So for example, look at this box here that I didn't want to spend too much time, because of course if you duplicate data you want to eliminate, that's quite straightforward. But think about if you have data that have a null, a zero, for many reasons. What do? You just leave at zero, and therefore in comparing 5-star, 1-star, they will be considered at zero, or you put an average on this data, or you eliminate the entire record because that will contaminate the data. So those kind of decisions are very important to increase the precision of the algorithm. There are techniques, advanced statistical technique. The most common is the median, but again, that is part of the data science. Well, even if the tool is so powerful, made things so easy, there is still room for humans to tune the meaning and the cleanness of the data to increase the precision. So yes, there are jobs like the recommender, a blockbuster, that have disappeared, but for every job a blockbuster, there is hundreds of jobs for data scientists that have been created. And that's pretty much, I would like to close this session and open up to questions, because we are 47 minutes into the call, and I know that there is generally plenty of questions, and I will be happy to address.
All right. So if anyone has any questions right now that are on their mind, feel free to post those in the GoToWebinar questions area, and we can get these asked and get some feedback. Right now, we currently don't have any questions pending.
All right, that probably means I was very clear. I simplified things very well. Actually, there were some questions that I received before the event on how many data sets can I include in the input data in terms of what what is a rating? Can the rating be the result of multiple data points from multiple point of view, and therefore creating your own meta rating? And I looked into the documentation, and yes, actually there are a lot of R libraries that do that kind of work to consolidate and harmonize different sources. And one of the beautiful things about Microsoft Machine Learning is that you can run R code, R library, and therefore you have an unlimited amount of tools available from universities and open source world. So it is a truly open environment.
Okay, well, we do have some questions here. Our first question is, how do you determine what % of the data needs to get allocated to the train versus the test data?
That's a good question, and I would say there are guidelines. At the end of the day, it's your call, and the guideline is how much is evaluating the accuracy important for you. Sometimes you need to put most of the data into the algorithm because you don't have much. And therefore, what you do is you move 95% of the data into the algorithm just to get the best accuracy, and then you rerun with another set, the previous algorithm. So there are way around, but the trade-off is the more you put into the algorithm, the less you're going to test it, and it's how risk adverse is your exercise that will make you decide how much you want to test it.
All right. Another question. Do you use the logistic regression as the model for prediction?
No, you could organize an experiment using logistic regression to establish probability. It would be very cumbersome and have a lot of work to do. There is a tool specialized for recommendations, and let's use it, the Matchbox. But yes, you could make an estimate of probability. It would be more cumbersome. That's it.
All right, this one kind of goes back to that allocation about the training and the test data. Is it possible, or could you set those both at 100%? And what would be the disadvantages of doing that?
Definitely not 100%, because if you put all the data into the development algorithm, you have no way to know if the algorithm has any precision. You might put 95% and keep yourself at 5%, but if you don't have a small set, you can't use it. You don't know if this is working well. You might have made an error some way that is not just the algorithm working, but a mistake on data cleaning, data preparation, and with having at least a 5% of data to test it, you will never know if there was an error. So I will discourage that.
Okay, so you can't have the train and the test data both be at 100%, correct?
Yes.
Okay. And next question is, can you share about possibly using machine learning to solve a practical problem for yourself?
Practical problem for myself. Okay, well, there are plenty of practical problems. Right now, we're using this for a restaurant chain to understand what kind of food to recommend in specials and different seasons, and we're trying to figure out what is that it drives this. Is it temperature? Is events and so on? Another experiment we did is for a large manufacturer. We looked at the data to predict if there was an opportunity to forecast if it was possible to produce a very difficult final product. And the reason is that if the final product is difficult and you fail, you need to do rework. It's very expensive. And generally, this is the kind of things that the expert makes a call. But once the complexity of the process becomes so high that the expert is no longer capable to guess right, this is the time where you want to use machine learning. So we looked at the data from the last 3 or 4 years, and we feature engineered the variables that were very likely capable to influence the capacity to produce this difficult product. And we tested several approaches. First, we did classification, and classification is the capacity to determine things like is this product in or out of the service level agreement, a yes or no, binary. Then we tried classification different level, like is this capable to be a product at level A, B, C, and D, so multi-class. And then we switched to further precision in regression. We say this product will have these characteristics at this PSI, at this quality. At that point, we were able to even give the customer the opportunity to plan for better products, because by optimizing the independent input variables, we could help them to project products that before was considered very almost impossible to do that. So those are two examples that I worked on successfully. And for the university, there is also another exercise on students at risk. How do we identify them, and how we make recommendations on what are the classes or the things that will make the students get out of the student risk and become a motivated students. So as you can see, we use the competency across different scenarios very successfully, and I encourage everybody to explore. And as a matter of fact, as a professor, I'm open to be of help. Therefore, feel free to reach to me on your experiments, and let's see if I can help. Here you have my email, you have my Twitter, and I think in about a month or 2 days, I will present another session that talks about another aspect of very common, and it's the churn. And churn is the science to study something that changes. A user that will switch carrier in a telecom world, that is probably the most common, but we use churn from another point of view. Once we know that the customer is very likely to switch, now think if you're even a restaurant, once you know that the customer very likely will switch and start going to another restaurant, how do I keep the customer loyal? I mean, it costs a lot of money to acquire new clients, so why don't we try to keep the customer that we have, the customer that we like? And so we're going to look into the algorithm to study churn, not just for switching from carriers, switching between retailers, switching between restaurants, but in a broader sense. I hope I gave enough examples.
Yes, definitely. Thank you. Okay, we've got 3 more questions here. First one, can you recommend any books for, like, say, a DBA that's interested in moving into this machine learning field? Any books or reference sites that would be helpful?
Yes, there is I don't remember the exact title, but it's using Microsoft Machine Learning. It's a second edition, and that was actually such a well-written book. If you reach out to me, I will give you the exact title. It's written by 2 Microsoft data scientists that were part of the development team. That is my favorite, especially because the examples in the book are I have experiments that are published in the Microsoft library of examples. So it's not theory, you just have real cases to work with. So
Perfect. Okay, next one. How would you choose between Azure machine learning or, say, like R enterprise solutions like Revolution R?
I would say that the two are not an alternative, they are complementary. Let me state that you could do everything that machine learning does in R. The issue is that it would be just difficult, cumbersome. It will take so much effort that you pretty much need to have a strong understanding of the algorithm and everything else. Vice versa, if you use machine learning, you gain productivity, you gain tools that are well integrated and harmonized to save time and let you think about the business other than playing around with code and trying what game do I do if I rewrite this part of the algorithm and things like that. So in addition, if you use machine learning, in addition to save time and focus on the business, you also still have the chance to take a library we call Carré from the R world and include in your experiments. As a matter of fact, Microsoft released very recently a couple of libraries that are very interesting. For example, in decision tree, you can load another library that will visualize the decision tree. And the difference is one, it says when you need to make a decision if a homeowner qualify or not, with this probability down into the tree of the decision tree, you see in the algorithm just the option, the probability. But when you see this visualized in a decision tree, it really helps a lot. So that is an example of another library I saw that adds visualization functionality to machine learning. And there are already examples of library that came from the open world that are well used in machine learning. So that's my answer. You can do both ways. In one way, you have a lot of help and a lot of productivity. In the other way, you can do whatever you want if you want to go in an exoteric algorithm.
All right, sounds great. Okay, just one. I don't know if this will be a quick one or not. If not, you can do a follow-up on Twitter or maybe a post. But just for clarification, someone's wondering, does the Matchbox, does that use a binary classification system, then uses mathematics to obtain the prediction? And if so, what is the mathematical formula that is used? Is that something that's published?
Okay. There are plenty of mathematical algorithms published into the R library world, and you can look at them. The one that I used within Microsoft Machine Learning, I think is a modification of an open source. The blog post that I include in the PowerPoint gives more technical details, but again, that is part of the things that a data scientist will dig in, and machine learning in this case gives you this as a well-packaged, optimized service. And when I say well-packaged, means that you can look at the mathematical formula and extract the 10 parameters will help you tune it. And so you just think about the 10 things, like the cold item means that you ever no information you want to accept as a starting point. You can say I can accept only 10 cold items, and therefore the precision is according to that. So you can use Microsoft Machine Learning to focus on the strategic decision you need to make to tune your experiment, or you can go into the 500 pages of algorithm and change the logic. If there are two different approaches. If you use machine learning, you should not be willing to go and change the logic. You should be willing to tune the algorithm for your usage. And if you want to see the logic entirely, use R.
All right. Well, thank you so much. Just wanted to quick remind everyone that there's the upcoming past business analytics content that's coming up in a couple of weeks, that past BA webinar marathon. Definitely check that out. And I want to thank you so much, Giuseppe, for presenting today. Really looking forward to your presentation next month as well, talking about how to be able to retain valuable clients. And I want to thank everyone for attending today. Please, when you sign off, please fill out that survey and give us some feedback. Thanks so much, everyone, for attending today. Any last minute words of wisdom or feedback that you want to give us? Giuseppe?
Well, just look at the experiments, the examples of experiments in Microsoft Machine Learning, and they're well documented, and just play with it. That's probably the best recommendation I can give.
All right. Well, thank you so much. Have a great day. Thanks, everyone, for attending.
Bye-bye. Thank you.